What's up, guys? This is Jahangir from Midporium, and today we're going to be talking about polarity and electronegativity. So let's start with polarity. And polarity is this idea that electrons in our covalent bonds, so covalent bonds aren't always equally shared. What does this mean? Well, when we're talking about polarity in a general sense, we're talking about opposite poles or opposite sides, you could say. And opposites always attract. You could think about the north and the south pole, or you could also think about magnets where you have that blue side, the red side, both of them attach, but they can repel if you're trying to get the north pole and north pole to attach. So pretty much the same thing. When we're talking about polarity, we're having this indifference in charges, indifference in attractions, which results in a ultimate attraction. Now, polarity in chemistry is really explained through electronegativity. So what is electronegativity? Well, this is the ability of an atom to basically pull electrons, or basically hog electrons. So this is really explained if we're looking at something like hydrofluoric acid, or HF. So we have H over here, and if we want to write our Lewis structure, that's there, and that's 1, 2, 3, 4, 5, 6. So we have 7 valence electrons in fluorine. We have 1 valence electron in hydrogen. This creates a bond over here. And let me actually make this bigger to illustrate what we're talking about. So this is hydrofluoric acid right here. And in electronegativity, we're increasing electronegativity going from left to right in the periodic table, with some of the most electronegative atoms being nitrogen, oxygen, and the most out of all of them being fluorine. So what happens when we have this electronegativity? Well, what happens is this fluorine over here, and let me change my color real quick. The fluorine over here is going to have a slightly negative charge, and this hydrogen over here is going to have a slightly positive charge. Now, also on the periodic table, our electronegativity increases going from down up. So going from something like rubidium all the way to lithium if we're talking about group 1 elements. That's when electronegativity increases. And here's illustrating the direction of our polarization. So this fluorine over here is really going to pull the electrons from the hydrogen, and we might see something like this structure where we'd have the fluorine having more pull on those electrons, and there's a better image to illustrate this, and I'll have it on the screen right there. But this is really illustrating electronegativity and how this polarity really creates a strong bond, a strong covalent bond between our nonmetals over here. Now, this is ultimately what's known as our polar covalent bonds. So polar covalent bonds. There are also nonpolar covalent bonds, and pretty much the opposite, where we're not going to have this unequal sharing of electrons. There isn't going to be one atom that's more electronegative than the other. So a nonpolar covalent bond might be something like chlorine gas, Cl2, where they're both the same elements. So there's not much of a difference in electronegativity because they have the same electronegativity, which is what makes them nonpolar. Now, the reason why we put this positive charge and negative charge is because this illustrates our dipole moment. So we'll put dipole moment. Now, dipole moment is a measure of separation between these negative and positive charges when we have in our polarity. So it really illustrates our polarity. And having a high electronegativity means having a high dipole moment, and vice versa. Now, talking about hydrofluoric acid, we're going to have a dipole moment of 1.82, and this is much larger compared to hydrochloric acid, which is only 1.08. So having higher dipole moment shows that we have more electronegativity, and this also means that we have a stronger covalent bond, because if we're more polar, we're having a stronger covalent bond. So with hydrofluoric acid, if we were comparing that to hydrochloric acid in terms of boiling point, hydrofluoric acid would have the higher boiling point because it's going to take much more energy to break away this bond, because a hydrofluoric acid is hogging those electrons from the hydrogen, and it doesn't want to let them go. Doesn't matter how high the temperature is. I mean, up to a certain point it would give it up, But compared to chlorine, hydrofluoric acid will maintain that covalent bond by pulling that hydrogen electron. So that's pretty much the basics of polarity and electronegativity, and knowing this will really help us understand other organic molecules. Now hopefully this video helped in any way, and as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.